guys to my first video about forces on a rocket. So today we're going to be explaining Newton's laws of motion and the forces they have on the rockets. The three most important being force of air resistance, force of gravity, and force of thrust. We'll go over each of these forces more deeply as we move along in the video. So starting off with the biggest force is force of thrust. The force of thrust is what pushes the rocket upward. It's what gives the rocket the oomph. Force of thrust is the biggest force until the engine of the rocket becomes obsolete. It doesn't work anymore. Like it's turned off. So it is pointed upward. So force of thrust. It is parallel with the rocket. So if the rocket were going at an angle compared to the Earth, it would be following the angle of the rocket. Then the second biggest force acting on a rocket is the force of gravity, which is what's pulling the rocket down. That's what makes us stay on the floor. The force of gravity is pulling it down, and it's going to be perpendicular with the ground. So as you can see, force of thrust was a little bit angled. Force of gravity is going straight down, perpendicular, which means 90 degrees with the ground. Just like that. Then one of the other forces we're going to be looking at, but might not use unless we're really going to try to get some precise measurements, is force of air resistance. Force of air resistance tends to be the smallest force, but it still technically matters if you're trying to get a very precise measurement. So force of air resistance, like we said with force of gravity, is going to go straight. The next force we're going to be looking at is the force of air resistance. If force of air resistance is the least strongest, it's the weakest force out of the three. It is entirely based upon the density of the atmosphere and a bunch of other things. It's the most complicated force, I will say, compared to the other three. Just like force of thrust, it's going to be parallel with the rocket but it's going to be what's pushing the rocket back. Imagine you're driving a car and you're going, or let's say we're dropping a piece of paper. The reason why, if you're dropping it flat, and the reason why it doesn't keep accelerating is because air resistance is pushing it back up. It's hitting those air molecules faster and faster until it gets to a certain speed, which is called terminal velocity, which is its maximum speed because the force of air resistance is equal to the force of gravity. So here we have force of air resistance pushing it back down. So this is a brief depiction or description of the forces on a rocket. Now we will dive deeper into what each of these forces look like. Starting with the force of thrust. Force of thrust, as we said earlier, is the biggest force out of all three forces until the engine of the rocket turns off or is out of fuel. Force of thrust is a little complicated because it involves it has a weird, it differentiates, it changes in force. So let's say you're driving a car. Your car's not always going to go the same speed. Sometimes you're going to accelerate, which makes the car go faster. And just like force here, it's changing. Sometimes it has a greater force, which makes the rocket accelerate faster than at different points. Just a standard common engine that we could be looking at is the Estes C5 engine, or the Estes C5 engine, whatever you want to call it. A common, not only for the Estes C6-5 engine, not only for this engine, but for a bunch of other engines, the graph looks very similar. We have the force of thrust, force of thrust on the y-axis, and then we got time on the x-axis. So as time goes on, we're going to be looking at how strong the force is. So for the Estes C6-5, we will dive into what exactly the numbers and the letters mean for the engines later on in different videos, but for today we're just going to be looking at the forces. So for the C65 engine, we are looking at a burn time of 1.6 seconds, 1.9 seconds, sorry. So that means that the engine is only burning for 1.9 seconds. And this is a solid engine, so once you light it, you cannot stop it. It will continue going unless its fuel source ends or there is no oxygen, because that is what a fire needs. Fire needs oxygen. So our graph is going to end at 1.9 seconds because there's going to be no more force of thrust because the engine will be turned off by then. So for a C65 engine, it's going to be, the graph looks like this. Really wonky and really a pain in the butt to work with because it's always changing. Here it's increasing, here it's decreasing, here it's staying the same, then it's decreasing again. And it's not increasing at a linear rate, it's not going in a straight line. It's a little bit curved, you can't really see it, but it's a little bit curved just like it's curved down here and curving down here. So it makes it a lot harder for the math. It would be much easier if it was just a straight line. But we don't get that. So the max thrust that we get for SC65 engine, I believe, is 15 newtons of thrust. You can also change that into pounds of thrust, but for the math aspect, it's going to be much easier just to stay with the metric system as well as newtons, because it's a whole other type of world with the imperial system. So the force of thrust is changing. Now let's look at the force of gravity. The force of gravity is what is pulling down the rocket. The rocket is being pulled down by force of gravity. As we said in the beginning of the video, we're going to be covering Newton's laws. And Newton's law states, one of his laws, one of his three laws states that the force is equal to mass times acceleration. Mass is the weight of an object. Measured in physics, it's measured in kilograms. Now, acceleration is not always the same. As we know that force is changing and the force of the engine is changing. So that means that the mass and acceleration, or the mass or the acceleration, must be changing, because if F is changing, M and A have to be changing. Let's say I have 5 candy bars, and then we'll just, here, look, 5 candy bars is equal to 4 plus 1. If I add another 5 candy bars, we have to do something to this side of the equation. We have to make sure it is equal to, in this case, 10, because 5 plus 5 is 10. So we would either add 5, or just change the 1 to 6, or we would change the 4 to 9. One of these variables has to change so it matches the changing of the force. So with gravity, we're kind of lucky. Acceleration isn't changing because gravity, unless we get to a really high altitude, gravity isn't really changing. Gravity, you accelerate to the ground at 9.81 meters per second squared, or meters per second, whichever way you want to say it. So that is A, which if you see it in the real world, some people might put it just mg, g meaning gravity, 9.81 meters per second squared. But the really weird thing about rockets is that the force of gravity is changing. But like I said before, gravity isn't changing because we're not launching these rockets high enough for gravity to change. So that means that mass has to be changing. Because the engine is burning fuel, some of that, the weight from the engine, the mass from the engine, is being lost in the exhaust. So we're losing weight, or mass. So that, because everything's changing, involves some calculus and stuff, but for the beginning of the channel, I think I'm just going to stick with algebra to make it much more simpler. So with mass, we're just going to take the average mass, and then with acceleration, we're going to take the average acceleration. Force of thrust, we're going to take average force of thrust, and then force of air resistance, we're going to take average force of air resistance, because it would involve a lot of calculus, and I know some people in the audience aren't really comfortable with math, and I don't want to put a whole lecture onto you for calculus when I'm already giving you a lecture on rockets. So, as we know, again, force is equal to mass times acceleration, but force of gravity is equal to mass times gravity, because gravity is the acceleration. Now, force of air resistance. The most pain in the butt force out of the three, because as we know, force is equal to mass times acceleration, but then some other forces are equal to different things, like centripetal force, or you'll mostly see force of air resistance written with some sort of constant times velocity. That is a much nicer version of what we're going to go over, but it's much more difficult to get to. So force of air resistance is defined, according to Wikipedia and many other resources, as 1/2 density, coefficient of drag, area in contact with air, the surface area from a bird's eye view of the rocket, multiplied by velocity squared. Now, the reason why we're not going to be really touching air resistance, because it's a pain in the butt, is because of this variable, v, which stands for velocity, or a synonym would be speed. Velocity in physics is measured in meters per second, but as most of you folks know, speed is measured in miles per hour. So in physics, for some reason, they really like the metric system. So we're going to be having to use some other units, which you may not be comfortable with, but I'm pretty darn sure that you will get the hang of it very soon. So, because of this variable, velocity. Now, what makes air resistance so mad because of velocity is because the speed of the rocket is changing. It's not always staying the same. As we know, it's accelerating. And when you press the accelerator on your car, the car speeds up. So we don't always have a constant velocity, and it's always changing. So we would have to have a very powerful computer or a whole buttload of calculus to always be inputting numbers in for velocity based on the acceleration at that point. If you guys are lost here, it is fine, because we're not going to be doing much of air resistance at the moment. I will cover it again once we introduce it back into our rocketry. So that is a little intro to each of the forces. If you have any questions, please feel free to comment down below, and I will definitely answer them, because I don't have many subscribers at the moment. But it's a lot, and please feel free to reach out to me and let me know if you have any problems with it. And then I will be releasing my next video over the equations of rockets, which involve kinematics and more of the fun physics. And I hope you enjoyed the video, and make sure to like and subscribe.